Hello and welcome back to Multidimensional Integration, the video series where we talk a lot about the Lebesgue integral in Rn. And indeed, in today's part 15, we will talk about the space that comes out there, the space of integrable functions, the L1 space. And moreover, we will show that the continuous functions with compact support lie dense in it. What all this means exactly I will tell you soon, but first I want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And you should know that as a Steady or Patreon member, you can download a lot of additional material for the videos, like PDF versions and quizzes. And then I would say, let's immediately start discussing the important space of Lebesgue integrable functions. And the common name one has for that is a curved L with power 1. And then next to it, one can put the domain and the codomain of the functions, and here we have Rn and C. This is the general case. We have functions defined on Rn, and they can be complex valued. And since we want to integrate such a function f, we know at least it should be a measurable function. And this just means that the preimages of measurable sets are also measurable. And this requirement tells us that the integral over the absolute value of f is well defined. So this is the integral over the whole space Rn with respect to the n-dimensional Lebesgue measure. And the notation we chose for that was just lambda with superscript n. So this is a standard Lebesgue integral which we can always write down if we have a measurable map involved. However, it could be infinite, and this is exactly what we don't allow for our L1 space. So here when we say integrable function, we actually mean that the corresponding integral over the absolute value is a finite number. And therefore in the L1 space, each function we consider here has a well-defined length, which we call the L1 norm. So this non-negative real number here is the L1 norm and denoted by a norm with index 1. However, now a problem is that this new object does not define a well-defined norm on this vector space. So it's actually not a norm simply because there could be non-vanishing functions that still have an integral of 0. And to get rid of this problem, one can simply go to equivalence classes of such functions. And the set of these equivalence classes is then denoted by a straight L1. Indeed, this is something you can always do when you have an equivalence relation given, and this one here is denoted by a tilde. And here I can also tell you that two functions are called equivalent if we can look at the difference in the L1 norm, and this one gives us 0. So in other words, if two functions only differ on a set with measure 0, then they both are in the same equivalence class. And in fact, this solves the problem. If we only consider equivalence classes of functions, then this L1 norm is actually a well-defined norm on the vector space. So from the mathematical point of view, this is much nicer, and therefore this is the space one usually considers as the L1 space. And I can also tell you that this one is actually a so-called Banach space. So simply a complete normed vector space. And at this point I should definitely tell you that usually one does not distinguish so much between these two different spaces. That's simply because we still want to explicitly calculate with given functions, but the statements we formulate in the end should hold for equivalence classes. Hence one usually jumps between these two levels, but actually it's never a problem. Okay, with this important definition out of the way, let's go to the next one, which is about continuous functions with compact support. So this is a vector space that we usually denote by a capital C with index C. And here the domain and the codomain are the same as before, so we are defined on Rn and complex values are allowed. And here I guess you already know everything, because first f should be a continuous function on Rn. And second, the support of f should be compact in Rn. And that's already it. This is our vector space CC. And if you have never seen that, you just need to know that the support of f is just the collection of all the points in the domain where the function does not vanish. Hence f of x is not allowed to be 0, And moreover, we always want that the support of f is a closed set. And to get this, we can just make it bigger and say that we consider the closure of this set. Hence, in this case, the claim that the support is compact just means that we have a bounded set in Rn for the support. So if you look at the graph of such a function, it's quite nice. Namely, if you're far away from the bounded support, then you're definitely equal to the constant 0 function. And on the compact support, it's a nice continuous function, so it cannot make any jumps. Therefore, we also should immediately see that the integral of such a function is well defined and definitely finite as well. So this set CC is clearly a nice subspace in the vector space L1. But maybe now more surprising is that the continuous functions with compact support form a dense subspace in L1. This means every L1 function can be approximated by such a continuous one. And this fact is really helpful in applications because the L1 functions can be really complicated, but the CC functions are quite nice, as you can see. Therefore, the statement now is definitely a very important approximation result. So it clearly deserves the name theorem. And as already mentioned, the statement is simply that CC lies densely in L1. And this approximation property is of course measured with respect to the given L1 norm. So we're not interested in single points, but just in the overall integral. So if you have never seen such a statement here, we should definitely discuss what it actually means. So if you fix a point in the L1 space, which is given by a function f, and if you also give an arbitrary distance, which we call epsilon as always, then you find a nice continuous function g that also should have compact support. And now the distance between f and g should be smaller than our given distance epsilon. And as already mentioned, the distance between two functions should be measured with respect to our L1 norm. So this is exactly what it means that the one space is dense in the other. Simply put, we can get as close as we want to any point in the bigger space by coming from the smaller space. And now for the rest of this video, we try to write down the whole proof of this nice theorem. So from the beginning here, we can just fix an arbitrary epsilon greater than 0 and an L1 function f, and then we want to construct a continuous function g that is close to f. And just to be clear, here we take an explicit function f, so if you want, a representative of the given equivalence class. And moreover, as a first case, I don't want to consider complex values, so let's stay non-negative. This makes everything a little bit simpler, especially our sketches, but at the end of the proof I will show you that this is not a real restriction anyway. Actually, the whole idea of the proof is quite simple, because we go in two steps, and the first one is to approximate our function f by a simple function. This should be possible, and a simple function only has finitely many values, so it's quite simple. And then in the next step, we try to connect the jumping points of the simple function to get a continuous function out. So this is the whole plan, and then we just have to guarantee that the changes in the continuous function we have here can be made as small as we want. But first, let's define the simple function, and I want to do it for every natural number m. And also for this definition, it might be quite helpful to do a sketch of the whole graph. So let's say here is the graph of our function f, and we know it does not have to be continuous at all. In fact, it does not have to be bounded as well, so it could be a quite ugly function. But the good thing is it's a non-negative function, so we can just partition our y-axis here to get a simple function. So the idea is simply that we have positive values and we can call them c1, c2 and so on. And our natural number m that is given should tell us how fine this partition is and where the cutoff is. So maybe let's say the distance between two values is just 1 over 2 to the power m. So increasing the number m should make the partition finer. And moreover, let's say that the last value of our partition is given by m itself. So this means here we continue until the numerator is 2 to the power m times m. And there we have it. These are the values that our simple function should have. And maybe if we want, we can also symbolically add the value infinity here in the end of the partition. This makes sense because now we have a lot of c's with the indices. And now, as you might recall from the definition of the Lebesgue integral, we have to look at the values of f. So for example, here we can look which points have values in this interval. And then we can define the simple function with the given lower value. And exactly this we can also do for all the other intervals as well. And please don't forget, we only have finitely many intervals given. So we definitely have a maximal value for this step function. And moreover, you might know that we can define such a simple function by using the corresponding pre-images here on the x-axis. So in general, we would call it aj, and it should be the pre-image of the interval under f. So more precisely, we put in the interval from cj to cj plus 1. And then j simply goes from 1 to m times 2 to the power m. Indeed, these are all the values we need to define the simple function Sm. Indeed, if x lies in the set aj, then the corresponding value will be cj. And in order to restrict the value to the set ai, we can use an indicator function denoted by chi. Another name is just characteristic function, and it just denotes a function that is 1 on the set aj and 0 elsewhere. And for that reason, we can write our simple function Sm as a linear combination. We just have to go from 1 to the last value, which is m times 2 to the power m. And there we have it. This is our nice simple function, and it's also clear it's defined for every m, and it always lies below our function f. Indeed, we should immediately state this as a nice property for Sm. First, no matter which point x we choose, f of x can never be smaller than Sm of x. And moreover, we can even estimate the distance between these two values if we know that m is large enough. This means if we fix a point x in the domain, we can look at the value f of x and make m larger than this value. This is always possible, and it guarantees that our x does not lie in the last aj. This means the symbol infinity is not involved in the interval there. And then we don't have any problem at all to estimate the distance between these two values. Namely, it's simply the distance between cj and cj plus 1. And there we know this is given by 1 over 2 to the power m. Therefore, if m goes to infinity, this distance goes to 0. And this nice property holds no matter which point x in the domain we choose. In other words, we have the pointwise convergence of the simple functions to the function f itself. And since the simple functions are dominated by an integrable function, we can apply Lebesgue's dominated convergence theorem. This is a famous theorem from measure theory, and it can help us a lot here. In fact, it tells us that the simple functions are integrable as well, and that they converge to the function f in the L1 norm. So this difference of the two functions in the L1 norm can be made as small as we want. And this helps a lot because now we can fix such a simple function that is close enough to our f with respect to the L1 norm. So from now on we will not change the integer m anymore because we will fix it such that this norm here is less than epsilon half. And as already mentioned in the beginning, in the next step we want to approximate the simple function Sm by a continuous one. And if we can do that with an error less than epsilon half, we are done. And now maybe first note that we have disjoint sets given by the pre-images. So all these aj's are actually disjoint sets in Rn. And by definition, they cover the whole support of our simple function. Or more precisely, if we call this union just A, then the closure of A is the whole support of Sm. And here you should note that this set can definitely be unbounded, but it's not possible that this set has Lebesgue measure infinity, because otherwise our simple function would not be integrable. So in general, the support of this simple function does not have to be compact yet. So this is definitely something we have to change for our continuous function in the end. So the first thing we could do here is to go to smaller compact sets in AJ. So if this is the sketch of AJ, then the compact set KJ lies inside. So this is clearly always possible in Rn, and we can also enlarge AJ to get an open set UJ. So this is not a problem at all. These two things clearly work for every index j. However, we can do even more because we know that the Lebesgue measure is regular. This means with respect to our Lebesgue measure, we can choose the compact set and the open set as close as we want to AJ. Or in other words, if we look at the Lebesgue measure of the difference of the two sets, it can be as small as we want. So for example, we can also make it smaller than epsilon-half. So there you see, this is the reason why we have proven the outer regularity and the inner regularity of the Lebesgue measure. So for any small number we want to have here in the measure of the difference, we can always find open and compact sets with these two properties. And indeed, as we will see later, this number has to be much smaller than epsilon-half. The thing that comes in here only depends on m, but the details are not so important right now. So first we will go to the left again, where we will define a continuous function that is exactly 1 on the compact set kj. And moreover, outside of the open set uj, it should be equal to 0. And then in between, it's possible to connect these two parts and we have a continuous function. This construction works in Rn and it's known as Urysohn's lemma. So you see, this is a really important result from topology and I have a whole video about it. So please check out my basic topology course if you want to know why this nice result holds. So here in this part we will just apply it, namely for every index j. So what we get is a continuous function gj that is defined on the whole space Rn. And Urysohn's lemma tells us that the values only lie between 0 and 1. And in particular, it has the value 1 on the whole compact set kj. And outside of the open set uj, it has the value 0. And clearly this implies that the support of gj lies in uj. Moreover, Urysohn's lemma also claims that this function can be chosen in such a way that the support is compact. And with that we almost have it. Now we just have to stretch and scale this function to cover the whole simple function. It simply means that gj should be scaled to the value cj. And then we just have to sum this up to cover all the different values. And as always, the last index is m times 2 to the power m. So if we just look at the compact sets, we are definitely equal to our simple function. So we have the equality for the whole union of the compact sets. And obviously this whole union is still compact, and here on the left hand side we have defined a new continuous function. And this one will be our final continuous function g. So this is our function that connects the steps in our simple function. So in a quick sketch it might look like this. So it makes sense to say that at most points this continuous function coincides with our simple function. Indeed, because of the overlapping open sets, we cannot guarantee that we coincide on all of the points of the compact sets. This means we have to describe this property more precisely, namely by saying what the exception set is. So we can guarantee this equality for every point x with the exception of a set E. So this is the exception set and it's where the overlap can happen. And by looking at the picture above, this is clearly uj without the compact set kj. So for just a single set this is quite simple, but now the point is that we have to go through all the possible overlaps. So we have a finite union of these intersections, and the thing is that some of them could slip into some of the other compact sets. But it does not really matter, because the Lebesgue measure of this exception set is really small. And the reason for that is that we could make these differences as small as we want. And now we just have to sum up this arbitrarily small number. So we get our epsilon-half in again, and now we can also understand why we had to add this factor with the dependence of m. simply because one part should cancel with the number of terms here. And the other part should just cancel when we look what can actually happen in the difference on this exception set. And since the exception set is so small anyway, we can do a really rough estimate. Namely, let's simply take the sum of the maximal values these two functions can have. For example, for g, we can just take 1 for all the subfunctions, which means we have the sum over the value cj. And there we already know each cj is definitely smaller or equal than m. And in the same sense, sm is smaller or equal than m. So in the end what we get is m squared times 2 to the power m plus m. And there you see, this is why we have chosen this factor as the value of the measure of the exception set. And with that we are definitely done, because now we can estimate the L1 norm. So what we want is g minus sm in the L1 norm, so this is a whole integral. So what we integrate is this difference here, and there we already know it's only non-zero on the exception set E. So we only have to integrate over E, and there we can use this estimate from before. And then as an estimate for the integral, we can use this maximal value times the measure of E, which tells us with the numbers from before that the whole thing is less than epsilon half. And now we can use that to finally calculate the L1 norm of g minus f. And this is quite easy because it's actually just a triangle inequality. The only thing we have to bring in is the simple function sm. And there the first part is less than epsilon half because of this calculation, and the second part we have already done in the beginning, and this was actually just the choice of our variable m. So in total we have exactly what we wanted, namely that this L1 norm is less than our epsilon. And please don't forget that the function g still has compact support, so the denseness is shown. The only missing explanation here is that the whole thing still works when our function f has complex values. However, this is not a big problem because we can just split the function up and use the argument from before for each part. So more precisely, we would have 4 different functions here that are all non-negative. And since we can always do this splitting up, the whole proof for the general case is already given. The only thing you have to do in the end is to build the function g from 4 parts as well. And there we have it. This is the end of the proof. So thanks for listening, and I really hope I meet you in the next video again. Have a nice day and bye bye.